Hi everyone, welcome back to the Reading Club. This is an ongoing series where I read papers on mixed integer programming and discuss the key ideas in simple language. So in today's episode, we are going to discuss this paper, which is called Restarting Algorithms. Sometimes there is free lunch by Sebastian. Right. So this paper actually discusses restarting algorithms for three different cases. So one of them is continuous optimization, which is basically gradient descent. Second is discrete optimization, which we will discuss. And the third one is submodular optimization. So where the objective functions are submodular functions and it has some nice properties and everything. So again, like these two are also very interesting, right? So they are kind of explained in a very simple language, but in this series, I'm going to focus only on discrete optimization. So in this video also, I'm only going to touch this part of this paper. Okay, so let's get started. Okay, so we will start with looking at our problem, which is let's say we are maximizing some objective, and let's say x belongs to some polytope p, and let's say x is binary 0 1. Okay, let's also say that c, our objective coefficients are all integers, uh, and not only integers, they are also all non-negative integers, right? So this is still we are not losing any generality, because if we have some negative objective coefficient, then we can just flip the coordinates, right? So if we have for some x we have negative coefficient, then we can just say that let's say x prime equal to minus x, and we optimize using x prime, right? So this is still kind of not really losing any generality. And now let's consider an augmentation algorithm, right? So let's say that we have some solution for this problem, some feasible solution, let's say x0, and we have this kind of structure. So the augmentation algorithm, it's very simple. Let's say we have an ability to find some solution that is better than this solution, right? So in that case, how do we reach to the optimal answer? It's very simple, right? So let's say we start with some x tilde, let's say x tilde equal to x0, and the idea is that we want to find some x which is in this feasible region, right? Such that my objective cx is better, right? So cx minus cx0 is greater than 0, or rather in different words I can say that c of x minus x0, this is greater than 0, right? So it is strictly improving my objective. That's what I want. And once I find it, then what I do, I'll just say that my new x tilde is x. Okay, and then I just simply repeat this. These two steps I just keep repeating. And once I have found my optimal solution, I will no longer be able to find this kind of an x, and that's where I'll stop. That will be my optimal x. So this is kind of very trivial algorithm. It's called augmentation algorithm. We just simply augment every solution and reach to our optimal solution. Now the problem with this is that let's think about how long it will take to reach optimality, right? So let's say how long till we find optimal, right? Any guesses? Well, it's kind of not so hard to figure it out, because our variables are all binaries, right? So there are at max 2 raised to n feasible points, and uh, if we in the worst case all of these points are feasible, in that case we can just strictly order them by their increasing values of the objective. In that case, we'll end up iterating through all of these 2 raised to n solutions, and in the worst case it can take up to 2 raised to n augmentation steps, right? So these steps, augmentation steps, to reach our optimal answers, right? So this is kind of a lot of steps basically, right? So it clearly exponential. Now it turns out that if we use a specific algorithm which is based on restart, which is called bit scaling, which we'll just discuss. So in that case, we can actually reduce this complexity to n times log of c, right? Where c is basically the largest coefficient in my objective, small c, right? So let me write it down. C is equals to, how do we write it? It's basically It's called the infinite norm. It's the largest coefficient of my C vector, right? So this is, yeah, we can basically find the optimal answer in just this many augmentation steps if we use the algorithm called bit scaling. So let's see what that is. Right, so bit scaling starts with this kind of breakdown, right? So we have our objective C, and what we are going to do is we are going to break it down into two parts, which is 2 times C1 plus C0, right? So what is C0? C0 is the last binary digit in my representation of C, and C1 is the rest of the part, right? So 2 times C1. Right, so basically what we can do is, let's say if we have phi in my objective coefficient, so then we can basically say that it is 2 times 2 plus 1. So C0 will always be either 1 or 0, nothing else, right? So if we have 6, then it is just 2 times 3 plus 0. Okay, so C0 is always either 1 or 0, and rest of the part is we can basically write it as 2 times C1. Okay, now here is the observation. Okay, so if we break our objective down into these two parts, and let's say if we have a solution, let's say x0, and if this x0 solution is optimal for this objective, right? So C1 objective, not entire C objective, but the C1 part of the objective, right? So if my objective is C1x, then x0 is the optimal solution for that. So from here, if I apply this augmentation algorithm, then I will, how long it will take me to reach the optimal answer for objective C. So let's try to find out, right? So let's say, so the objective, the augmentation part was that we needed to do this part, right? So C times x minus x0 should be greater than 0, right? So it should strictly improve, right? So if it is strictly improving and x0 is the optimal answer for this C1, then what is this part, right? So C times x minus x0, x minus x0, right? So this is same as we can just write it down as 2 times C1 of x minus x0 plus the rest of the part, which is C0 times x minus x0. Now x0 was optimal for C1, right? So this part, C1 times x minus x0, which is improvement in the C1 part, is not going to be there because x0 was the optimal. So this part has to be less than or equal to 0. And now the remaining part, this part. So what is the largest this part can get? So again, like notice that C0 is only ones and zeros, right? So no matter how I change it, we have only n variables. So it is always going to be less than or equal to n. So in either case, what we have is that my C, the number of improvement steps I can have is definitely going to be less than or equal to n, right? So every step I'll improve C0 by 1 and assume that C1 stays less than or equal to 0. In the worst case, I'll have at max n improvement steps. So if I start with x0, then the augmentation algorithm will find the optimal answer for C in at max n steps, right? So that's the observation. So the key idea is that we have to break it down into these parts. And the second key idea is that we need to start with an optimal answer for C1, right? So this is the tricky part. This is where the bit scaling comes into effect. Okay. So let's see how do we do the bit scaling part. Okay, let's erase most of the part, but I want to keep this part. So let me rewrite this part down again. C equal to 2C1 plus C0, and x0 is optimal for C1. Okay, so from here we can get the optimal for C in n augmentation steps. Okay, so how do we start our algorithm? It's basically simple, right? So we are going to do bit scaling, which is something like this. So let's say we have our largest objective coefficient, right? So and let's represent it in binary, right? So let's say it is something like this, some random representation, right? Let's say it is this the number, which is my largest objective coefficient. So what I'm going to do is that I'm going to I'm basically going to ignore all of this part, and I'm only going to consider the most significant bit, which is this one, in my entire objective, right? So all of my objective coefficient, I'm going to divide by 2 raised to, what is this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 raised to 10, I'll divide it by 2 raised to 10. So all of this part will be gone, and my objective will have only ones and zeros, right? So this is the largest objective. The other objective coefficients are smaller than this. So for them, they will be either 1 or zeros are left, and mostly it will be zeros, but some of them will be still ones. And so in this case, what we have is this kind of scenario where C1 is equals to 0 and C zeros are left, which is like the, so I'm basically now going to optimize only over this part, right? So this part, which is my C0. Okay, and as we know that it is only going to take me at max n augmentation steps, because there are only n different values for this objective. So it's kind of very easy to optimize over. Okay. So let's say after this first step, it is going to take me at max n augmentation step, and this is where we do the restart, right? So after this, we have our x0, which is optimal for this part of the objective. Now what we are going to do is we are now going to look at the first two most significant bits, right? So this one and this one. So again, now my objectives are basically 2-digit binary numbers, and some of them might be zeros, some of them might be ones over here, and we don't care. So now again, like, we go for this part of breakdown, right? So this two bits, we're going to break it down. So first bit is here, and the second bit, which is C0, is here, right? So we have already found an optimal answer for this C1 objective, right? So C1 objective was this part, so only this part, which is our x0. We found it in the previous iterations, right? So with using n augmentation step. So again, like, if we try to find the objective answer, the optimal answer for this 2-bit objectives, then it's going to take at max again n augmentation steps. Okay, so this is kind of trivial. So we have, let's say, x1, which is optimal for first 2 bits, and now we just keep on going like this. So now we go on and find the optimal answer for the first 3-bit objective, right? So everything else is still 0, right? So how do we achieve all of this? So it's basically very simple. We just set C mu. This is the objective that we'll be optimizing for, and that is basically the original objective divided by some mu. And what is this mu? Mu is basically the most, so 2 raised to whatever some power, right? So 2 raised to, what is the power? It is basically the largest, so how many digits are there in my largest objective coefficients, right? So it is basically log of this capital C, and let's seal them. Okay, so everything has to be integer. So this division is also integer division. There are no decimals involved here. Okay, so we just keep doing like this, and after every restart, after every time we find, first time we find x0, second time we find x1. So after that, we just simply divide mu by 2. So this is my new mu, right? And then again, like, we just go like this. So all of this, after every restart, it's going to take me n augmentation steps. And how many restarts I'm going to take? It will take me so n augmentation steps, and number of restarts I'll take is basically log of C, the number of binary digits in my largest objective coefficients, which is log C, right? So as we promised, so this is the complexity, right? So in fact, it is basically this, right? So it doesn't matter if we put a seal or not, but yeah. So this is kind of interesting, right? So it's by using this kind of bit scaling, we can just simply bring down the complexity from 2 raised to n log C. So it's not actually the complexity, because this, I don't know how long this augmentation step takes, right? But it actually helps. It requires fewer augmentation steps, and this way the restart algorithm is kind of very helpful. Okay, so now we'll see another restart scheme which is very similar to bit scaling. It's called geometric scaling. Okay, so the idea is that we will define another objective which is C mu x x tilde, right? So this is the solution on which we want to improve on, and so this goes like C times x minus x tilde, which is how much am I improving over x tilde in objective, plus mu times x minus x tilde, and it's 1 norm. So it's basically how many bits am I changing in my solution, right? So this is the new objective. This is the objective we'll be giving to our augmentation algorithm, right? And every time we will basically change the mu, and it's basically simple, like same as the bit scaling. It says that every time we will halve the mu, right? So first time it is mu, second time it is mu by 2, third time it is mu by 4, and so on and so forth. Okay, so let's say if we started with some solution, and x tilde is the optimal answer that we got after one iteration, one set of iterations for C mu, right? So in that case, basically for every x, this objective will be less than equal to 0, right? Because x tilde is my optimal answer for C mu using my augmentation algorithm. Okay, so for other x, it will be less than equal to 0, right? So it's by definition. And now let's talk about C of mu by 2. And let's say if we are if we are still like operating in the augmentation algorithm, and let's say at some iteration we found this x plus solution while improving over this x prime solution, right? So in that case, so what we'll have is that C of x plus minus x prime plus this is mu by 2 and the one norm, right? So x plus minus x prime. So this part has to be strictly greater than 0, because this is what we got at the end of one iteration of augmentation algorithm, right? So it is x plus is strictly improving over x prime on C mu by 2 objective, which is this one. Okay, and now let's try to combine these two inequalities, right? So from this inequality, what we can get is that 2 times C of x plus minus x prime divided by this part, which is norm of x plus minus x prime. This is strictly greater than mu, and from this one we can say that mu is greater or equal to all of this. So C times x minus x tilde divided by norm of x minus x tilde, right? So nice little objective. Now this is actually true for all x, right? So this is something that we got at the end of our augmentation algorithm. So x tilde is the optimal answer for C mu x minus x tilde, right? So this is true for all x, right? So it is not true for like every x. So if you consider the optimal x for the original C objective, right? So let's call it x star, right? So original C, the optimal answer is x star, right? So the in that case also it is still true, right? So it is this, and under this, if we put x instead of x, we put x star, this inequality still holds, right? So x star is not the best solution for this objective. It is the best solution for this objective. So we can actually replace x by x star also here. Okay, and from these two inequalities, what do we get? Let's get rid of this mu. Then we can say something like C of x plus minus x prime, right? This is greater or equal to 1 by 2 times this norm, which is x plus minus x prime divided by with this part, x star minus x tilde. Okay, and this part, remaining part, which is C of x star minus x tilde. So you can see why I put x star here and x tilde here. So we are starting with x tilde, and x star is the optimal answer for this C objective, right? Our original objective. So what is this? This is basically the primal gap, right? And what is this? This is the improvement we get in one augmentation step, right? So if we can find out what this quantity is, so then we can basically bound what is the improvement. We can lower bound our improvement in terms of our original primal gap. Okay, so let's see. So this part, which is the norm, right? So how many bits am I changing from one step, which is at least we have to be changing at least 1 bit, right? Because we are changing the different solution. The improvement has to be strictly greater than 0, right? So this part is at least 1, and this part, how is the largest this part can take, which is in case of binary it is at max n, right? So there are only n bits we can change, right? So they are both 1 norms over here also, right? So all of these are 1 norms. So this part is basically saying that 1 over 2n times primal gap. Right? So every improvement step, I will be at least improving 1 by 2n times primal gap. So in other words, if I apply this improvement steps 2n times, at max 2m times, then I will basically cover all of my primal gap. Right? So I would not need more than 2n steps to cover all of my primal gaps. Right? So that's the idea, and that's basically says that I'll at max need 2n times augmentation steps, individual augmentation steps, and how many times I'll have to do this mu by 2 restarts. That part is kind of complicated, right? So they haven't actually mentioned in the paper, but over here they said that they start by mu equal to nc, where c again is the largest objective coefficient, right? And so every time they basically start with this nc and then uh, divide mu by 2 every time. So overall it will take order of n time log nc augmentation steps, right? And it turns out that in the paper they have said that if we do some more math, then basically we can get rid of this n. So it is same as the bit scaling algorithm. So it turns out that this geometric scaling algorithm, it can actually be even generalized for general integers. They haven't actually showed us how, because they wanted to keep things very, very simple. And so, yeah, this is another scheme where, we can basically use restarts and we can transfer information, and using that we can basically achieve very nice guarantees. So recall that the original augmentation algorithm, it would take 2 raised to n augmentation steps, right? So compared to that, all of this is quite small. Okay, so we saw two restart scheme. One of them was bit scaling, and the other one was geometric scaling. Okay, so both of them basically improved the performance quite a lot. So in terms of theoretical guarantees, we actually got better guarantees, and this we could get because we were actually transforming some information, right? So in bit scaling, we first learned the optimal answer for initial few bits, and then once we have had this answer, then we could apply it to uh, the next set of objective, which is this part, right? So all of this plus an extra bit of objective. In that case, we can actually transfer all the information that we learned here to get the optimal answer for this one, right? And similarly here also we are basically transforming some information so that it is actually helping us reduce our iterations, overall number of iterations. So there are many other places where this kind of restart schemes are applied. So one of the example they have given in the paper is Chavatal-Gomori cuts over this polyhedron, so 0, 1 raised to n. Right? So in this case, they have said that the actual guarantees could be actual guarantees for how long it will take, how many CG cuts will be needed to reach the convex polyhedron. That can be significantly reduced by using this kind of, not exactly this, but similar restart schemes. So they haven't actually given the details, but they just mentioned that this is kind of similar things have been done in over here also, right? So hope this was kind of useful, and see you in the next video. Bye.